Imagine a magical box. We'll call it the function machine. You put something in. The machine changes it according to a rule. Then it spits something new out. That's what a function does in math. It takes an input, transforms it using a rule, and gives you a unique output. Think about a toy car factory. Each toy car or input goes through the factory's machines. They get painted a specific color, the rule. A shiny new red car comes out the other side, the output. This process, like our function machine, always follows a specific rule. Every input leads to a single predictable output, just like our factory makes only one car per input.
In the language of mathematics, a function is a special relationship between two sets. We call these sets the domain and the range. The domain is like the input set, containing all the possible values you can put into the function. The range is the output set, containing all the possible results you can get. Here's the important part. For a relationship to be a function, every input from the domain can only have one output in the range. No two-timing allowed. This ensures that for every input, we always know exactly what output to expect. Let's go back to our toy car factory. Imagine putting in a toy car and getting a red car out one time, then a blue car the next. That wouldn't be a function. Our function machine, just like a well-run factory, needs to be consistent and predictable.
Now, just like ice cream, functions come in different flavors. Let's talk about 3: injective, surjective, and bijective. Don't let the names scare you. They're simpler than they sound. Injective functions are like giving unique name tags to each student in a class. Each input has a different output, so no two students get the same name tag. Surjective functions are like making sure every house in a neighborhood has a mailbox. Each output in the range has at least one input in the domain assigned to it. Now imagine a function that's both injective and surjective. That's a bijective function. It's like a perfect matching game where every input has a unique output, and every output has a match.
Section 4. Mapping the relationship representing functions. Functions are like secret codes, and we need ways to crack them. We can do this using equations, ordered pairs, and graphs. Equations are like the rule book of a function. They tell us exactly what operation is being performed on the input. For example, the equation y equals 2x says that we double the input value to get the output value. Ordered pairs are like a list of input-output combinations. They tell us which input corresponds to which output. For example, the ordered pair 2, 4 tells us that when the input is 2, the output is 4. Graphs are like visual representations of functions. They show us the relationship between the input and output using a coordinate plane. By looking at the graph, we can see how the output changes as we change the input. Each of these representations helps us understand the function from a different angle, just like having different tools to solve a puzzle.
Section 5. The usual suspects, common types of functions. Just like superheroes, functions come in different forms, each with their own special powers and abilities. Let's meet some of the most common types. Linear functions. These are the straight talkers of the function world. They always create a straight line on a graph. Think of a steady pace on a bike ride. Quadratic functions. These functions like to make things a little more interesting with their curves. They create parabolas on a graph, like the path of a ball thrown in the air. Exponential functions. These functions are known for their rapid growth or decay. Think about the population growth of bacteria or the decay of a radioactive substance. Logarithmic functions. These are the detectives of the function world, helping us solve for unknown exponents. They're like the inverse of exponential functions, trigonometric functions. These functions involve angles and ratios in triangles. They're like the navigators of the math world, helping us understand relationships in circles and triangles. Each of these functions has its own unique personality and uses, making the world of mathematics a diverse and exciting place.
Section 6. Functions in action, real-world applications. Functions are everywhere in the real world. They're not just stuck in textbooks, they're out there making our lives tick. Engineers use functions to design bridges, buildings, and airplanes. They need to make sure that their structures can withstand various loads and stresses, and functions help them model these forces. Doctors use functions to understand how our bodies work. They use them to model things like blood flow, heart rate, and drug absorption. This helps them diagnose and treat diseases more effectively. Economists use functions to model economic trends like supply and demand, inflation, and market fluctuations. This helps them make predictions about the economy and advise businesses and governments on economic policies. Even video game developers use functions to create realistic movements and interactions in games. Every time a character jumps, runs, or shoots a weapon, there's a function behind the scenes making it happen. Functions are the unsung heroes of our world, working behind the scenes to make things work the way they do. Understanding functions helps us understand the world around us better and solve problems in all sorts of fields.